The Physics of Interstellar Travel, Chapter 14, Navigation. A spacecraft needs to know where it is heading, and how fast it is moving. Such navigation is necessary so that the spacecraft can turn on its instruments at the right time, point its communication antenna in the right direction, and make course corrections. Techniques for navigation are well developed for spacecraft in the solar system, but new methods are needed for deep space. But before we consider interstellar navigation, let us first look at how we navigate within the solar system. A common method, also used by ships and aircraft, is called dead reckoning. If you know your speed, then simply measuring the elapsed time tells you how far you have travelled. If you knew your initial position and direction of travel, then you will know where you've got to. In reality, though, your velocity, speed and direction will change over time. Changes in speed can be measured without any external reference using an accelerometer. This is essentially a mass on a spring that measures the acceleration. When this acceleration is integrated over time, we get the change in velocity. To also determine direction, one can use a gyroscope, the mechanical version of which is a massive spinning wheel that retains its orientation in space whilst the vehicle rotates around it. To integrate the acceleration measurements, we need an accurate clock. In spacecraft, atomic clocks are often used on account of their high accuracy of around 1 part in 10 to the 12, which is equivalent to 30 microarcseconds per year. Accelerators and gyroscopes are often combined together into a so-called inertial measurement unit. Many smartphones have them, and they are used in spacecraft. The major limitation of inertial navigation is that measurement errors of acceleration and direction accumulate with time, so this method can only be used to determine the change in position and velocity over short periods of time. We must periodically determine our position and velocity in some global reference frame. In deep space applications, such absolute fixes are usually obtained by sending a radio signal from a ground station on the Earth to the spacecraft and back. The signal travel time tells us the distance to the spacecraft, or its range. With a large antenna and measuring over a long time, the range can be determined to an accuracy of 1 meter. The Doppler shift of the signal tells us the line of sight velocity, and this can be determined extremely well to around 0.1 millimeters per second. The angular position of the spacecraft in the sky is poorly constrained by such ranging methods, though, due to the limited angular resolution of a radio telescope. Angular position can be determined more accurately by using 2 ground stations with a method known as differential one-way ranging, or DOR. In this method, a signal is sent from the distant spacecraft towards the Earth and is received by both ground stations, A and B, in this figure. The difference in the arrival times of the signals is delta t, and because we know the distance between the 2 ground stations, simple trigonometry gives the angle to the spacecraft, shown here with theta. The second angular coordinate is determined using either a 3rd ground station or by waiting for the Earth to rotate to reorientate the baseline AB. A more accurate version of this method is known as delta DOR. This measures the angular positions only relative to a distant quasar, which has a very accurately known position. Delta DOR is often used for interplanetary missions and can achieve an angular accuracy of half a milliarcsecond, which corresponds to a distance of 1 AU of 350 meters. An interstellar spacecraft will be too far from the Earth for such ranging methods. The signals will be too weak and will take too long to arrive. Interstellar spacecraft must therefore navigate autonomously. One way to do this is to use the stars. As seen from the Sun, the stars have certain fixed positions. As we move away from the Sun, and because the stars are at finite distances, their relative positions will change due to parallax. Assuming we know the precise 3-dimensional positions of the stars as seen from the Sun, these changes are predictable. Putting it the other way around, by measuring changes in the stars' positions, we can determine where we are relative to the Sun. To do this, we do not need to measure the 3-dimensional positions of the stars from the spacecraft, which would be very hard. We don't even need to measure their 2-dimensional angular positions. It is sufficient just to measure the angular distances between pairs of stars, a 1-dimensional measurement. Provided we measure enough of these, we can uniquely determine the spacecraft's position. One complication, however, is that the spacecraft is moving. As we learned in Chapter 9, this means that the positions of the stars will be displaced due to aberration. As we don't know the spacecraft's velocity, how can we disentangle the aberration displacements from the parallax ones? Fortunately, these two displacements are in opposite directions, as you can see in this sketch. The parallax also depends on how far away the star is. The aberration does not. It turns out that if we measure enough stars, about 6, then we can disentangle the effects of parallax and aberration. Moreover, we can exploit this aberration to determine also the velocity of the spacecraft. The upshot is that we can determine both the three-dimensional position and the three-dimensional velocity of the spacecraft just by measuring the angular separations between pairs of stars. The equations involved in this are nonlinear, so we need to use an iterative method to do this, as summarized in this diagram. A key input to this method is the three-dimensional positions of nearby stars relative to the Sun, which have been determined to high accuracy by the European Space Agency's Gaia mission. The limiting factor is how well we can measure the angles between stars from the spacecraft. If we can measure them to 1 milliarcsecond accuracy, 1 mass, then using 10 stars, we can determine the spacecraft's position to 0.01 astronomical units and its velocity to 10 meters per second, even when the spacecraft is moving at relativistic speeds. A different method of navigation is to use the regular radio or X-ray pulses sent out by rapidly rotating neutron stars, or pulsars. The direction of the pulsar from the Sun is very well known, as is the period between the pulses, so we know exactly when the pulses arrive at the Sun. If the period is very long, then when the spacecraft receives a pulse, it can compare the pulse's time of arrival with the expected time of arrival at the Sun. This difference tells us the projected distance from the Sun, the distance a in this figure, although it doesn't tell us the angle theta. So this constrains the spacecraft's position to be somewhere on a plane. However, the pulsar period is not very long, so when the spacecraft receives a pulse, it does not know when this particular pulse would arrive at the Sun, as all pulses are identical. What this means is that the spacecraft can only constrain its position to be lying somewhere on one of many planes separated in distance by the light travel time between pulses. So far, not very useful. But when we now use a second pulsar lying in a different direction, this constrains the spacecraft to lie on another set of planes inclined to the first, and with a different separation in general. Their intersection, the intersection of these two sets of planes, is a series of parallel lines going in and out of the screen. This is getting better. With a third pulsar, the intersection, the possible spacecraft's position, becomes a set of points, the intersections of all these lines. There still remains some ambiguity between these different possible points, but if we have a reasonable initial estimate of the spacecraft's position, for example from astrometric navigation, this can be resolved. Pulsar navigation has been tested in Earth's orbit by both NASA and the Chinese Space Agency, showing that positional accuracies of between 10 and a few tens of kilometers can be achieved. The principle of pulsar navigation has some relation to global navigation satellite systems, such as GPS and Galileo, and I describe this connection in the chapter. Determining one's position and velocity in deep space is essential for interstellar travel. This has to be done autonomously, using only observations that can be made from the spacecraft without any reliance on the Earth due to the large distance of the spacecraft from the Earth. Course corrections are then straightforward if the spacecraft has rockets, although options are more limited for sailcraft. Check out the chapter for some possibilities.